Hey everyone, Mr. Skelton here. We are back at it for the last lesson in Unit 1, and this should be a 5. This is our Unit 5, not Unit 7. I'll make that change for you there. This is Lesson 5 in Unit 1. Today we're going to talk about graphs, and specifically we're going to talk about the graphs of absolute value functions, okay? And we're going to focus on this. And the slide right below this says parent functions you may already know or soon will know. Most of you know a linear function, right? We usually see it in this form, y equals mx plus b. You were probably exposed to some quadratic functions back in Algebra 1, okay? And that's like anything x squared. Anything x squared is a quadratic. You probably saw some things like this. X squared plus 3x minus 9. That's an example of a quadratic. When you graph that, it becomes a parabola. These two you definitely saw in Algebra 1. The rest, I doubt you have seen yet. Now, you may recognize some words and maybe some symbols and things like that, but we will get to all of these eventually throughout the year. To be honest with you, Honors Algebra 2 and Algebra 2 in general is really just a study of different kinds of functions. And throughout the year, we're just going to be hitting these one after the other. For example, right now in Unit 1, we're focusing a lot on linear functions. We've done some y equals mx plus b, and we've done some graphing of those, writing equations of linear functions. We have a whole nother unit on quadratic functions coming up. We'll get into exponential functions and radicals and logs as the year goes on. But again, Honors Algebra 2, really just a study of functions, how they work, and then you're going to be graphing each of these type of functions, and that's what we're going to get into today. Now, the one function that you don't see in this list is right here. I have it at the bottom, which says, however, today we're going to be primarily focusing on one function, which is the absolute value. Why are we putting this in Unit 1? Well, we spent some time solving problems like this, right? 3x plus 2 is equal to 5, right? And we've been solving those type of absolute value equations in Unit 1, so we thought we'd introduce the graphing of those functions as well. So let's turn the page and let's get started here. So on the very top slide, a lot of this is already graphed for you, so you're just going to have some nice visuals here, and I'm going to kind of explain things as we go. It says, let's start by learning what the graph of the parent function looks like. So absolute value graphs, absolute value. I always remembered the shape of an absolute value graph because it had a V for value, right? The letter V. And absolute value graphs will always be V-shaped, okay? Now, they'll go up like this and on forever. You'll notice the arrows on the end. And you'll see here as we go through the video that they can also be flipped upside down, all right? And so we'll get to that towards the end. Now, how does this work? Why are they in the shape of a V? Well, if you remember, with absolute value, you would break this off into two equations, and you basically get y equals x and y equals negative x, right? And what's the slope? The slope, or what, if you take this equation, y equals x, how would you graph that? Well, you'd graph that from a slope-intercept of 0, that's why it starts at 0 here, and then the slope would be 1 over 1. So you go up 1 over 1, you can see that point there, up 1 over 1, up 1 over 1, up 1 over 1, etc. Well, with absolute value, you know, when you write your two equations, you get this to be x equals negative x. Well, again, where's the y-intercept? It's really at 0, and then the slope is negative 1, which would be up 1, left 1, up 1, left 1, up 1, left 1. So it should make sense to you why absolute value graphs are in the shape of a V, because they come from two different linear equations. That's what's kind of nice, and that's kind of why we pair linear equations and their graphs with absolute value. I made a t-chart for you here. If you plugged in all these x values and took the absolute value, you'd see the resulting y values as an output. So this is what we call the parent function. It's the basic function, okay? There's no numbers added to it, no numbers subtracted, there's no multiplication. That is the parent function. And what we're going to do in this video is we're going to move or shift this V graph around the coordinate plane. So let's take a look at some examples, and I'll talk through them briefly, and you'll be able to kind of see what's happening. So it says on the left, now we'll change the parent function and see what happens. So in the equation, you have the y equals absolute value of x plus 3. So the parent function is the shaded graph here, which we just went over, starting at 0, 0. What do you notice that happened when you have addition outside of the absolute value bars? You should notice that all it did was shift your y values. Remember, this is the y-axis running up and down. It shifted all the y values up 3 units, 1, 2, 3. And you can see that here. This is the parent function t-chart right here. So these two, that x and that's y. That's the parent function t-chart that's just directly above in the slide above. And you can see when I add 3, if you plug in these x values, negative 2 in here for x, you get absolute value of 2, plus 3, you get 5 as an output. And you can go to negative 2 and go up 5, and you can see these points. So this x value here and this y value here is a result of the function y equals absolute value of x plus 3. Here's what you need to know. Any number that is on the outside of the absolute value bars, any number plus or minus, and we'll talk about negatives here in a second, that's on the outside is going to shift up or down the number of units that are shown. Plus 3 is on the outside, up 3 units. Okay? Let's go to the next page. So on the next page, you see what happens when there's a negative outside of the absolute value bars. Okay? Over here, we kind of I have written down for you what we just kind of concluded. When you add or subtract after the operation translates the graph up or down, meaning anything outside of the absolute value bars is going to be true and you'll shift it up or down. So in this case, because it's a minus 2, it'll shift down 2 units, the whole graph. And you can, again, you can test that by plugging in your points and you can see the result of your resulting y values right there. So now we're going to change gears a little bit. Here's the function. We have y equals the absolute value of x minus 3, but the minus 3 is inside of the absolute value bars. And so again, this is the parent function, t-chart. Right? And this is what happens when I want you to focus on your x values and how they shifted. I want you to compare these x values in the shift that's taken place. So these are the x values after the shift. You'll notice, I mean, you can see with the naked eye, starting at 0, and everything on this parent function graph has shifted to the right 3 units. Okay? You're going to see on this next slide, I have right here the plus 4 inside of the absolute value bars. Now on this graph right here that I'm kind of outlining with my pen, that is the graph from the previous slide. This graph right here was the y equals absolute value of x minus 3. Okay? This graph right there, where I shifted to the left 4, is the y equals x plus 4. So what pattern can you pick up? Here's the conclusion. Adding or subtracting, okay, a number before the operation translates the graph to right or left. In other words, any number that's on the inside of the absolute value bars is going to shift to the right or to the left. Now, how do you know which is which? Well, here's a way to figure it out. If it's a plus 4, we went to the left, negative 4 units. On the previous slide, or you can just look right here, I have a minus 3 and it shifted it to the right 3. So what a lot of students always remember is always the opposite movement, meaning if you have a positive 4, you're going to go negative 4 or to the left 4 units. Okay, put it to you there. This one was x minus 3, so you're going to go to the right 3 units. That's that shift. Okay, moving on. The bottom slide here, you'll notice there is nothing inside the absolute value bars. There's nothing added or subtracted on the outside. What do we have? We have a number, in this case 2, that is multiplied by the absolute value bars. And think about that for a second. After you take the absolute value of something, whatever this is, and you multiply it by 2, what's going to result as your y value? It's going to double, right? You're basically taking whatever number you plug in for x, and you times it by 2, it's going to double to 4, right? When you take 1 and you plug in negative 1 to the absolute value, it gets 1. 1 times 2 is 2. So what happens, all of your y values, or what we call your outputs, double. And so what happens to your parent function, remember the parent function here is in gray, what happens to this is it gets stretched. We call it a stretch. When you have a number in front, and I'm going to tell you the term that we use, it's called a scalar, and you'll see it on the next page, but I'll give it to you now. A scalar. When you have a scalar or a number above 1, okay, a number above 1, you're going to get what's called a stretch. And that should make sense. If this was a 3, what would happen? Your y values would be multiplied by 3. And so it's going to get skinny, right? It's going to get really narrow. Your graph is going to get, we call it a stretch. It gets stretched up top, and it kind of comes together a little bit because your y values, it was 1, 1, now it's at 1, 2. Everything got multiplied up. All right? So let's turn the page. So here is an example. I just talked about this one. I forgot I had one with a 3 on it. So what happens to your y values? They all triple. You plugged in a negative 2 for x. You got 2. Multiply it by 3, you get 6. So here's your parent function right here. This was what happened when it doubled, and here's what happens when it triples. Okay? 1 goes to 3, 2 goes to 6, 3 goes all the way up to 9 or off the graph. But you can see how when there's a 3 in front compared to the 2, this was the y equals 2 times absolute value of x, it's more narrow than this one because this number is larger than 2. So the larger this number gets, the more narrow, or what we call stretched, the graph will become. Okay? When multiplying by a number, which we call a scalar, the graph gets stretched vertically. I like to add vertically in there. Okay? Stretch gets, I think I put too many L's in there. Stretch vertically. Okay? Now, so remember, I said numbers, when it gets stretched vertically, that has to be above the number 1, above 1. So anything above 1, 1, or 2, 3, 4, 5, 1.5 would stretch things vertically. So what happens when your scalar is less than 1? What's going to happen? Well, let's take a look. So here's the parent function in gray. Right? Everybody can see that. And then you have, this was your y equals 2 times absolute value of x. This was y equals 3 times the absolute value of x, and you can see that our graphs got more narrow. So this right here is the graph of the function that is listed, which is the 1/2. So what happened? Our graph didn't get narrow. What happens when you multiply anything by a half? It's going to get, your output is going to get cut in half. So now when you plugged in the 2 for x, 2 now becomes a 1 because everything is getting multiplied by 1/2. What's the result that it looks like on a graph? We call it a shrink. Okay? Sometimes squeeze or shrink, we use the word shrink a lot. It's getting more wide, if you will. It's kind of flattening out, right? Right here. It's kind of widening out. So anything less than 1, a half, a fourth, a third, is going to widen, or what we call shrink. A lot of times you hear the two words stretch and shrink. Okay? Stretch and shrink. Stretch is when your a value is above 1. Shrink is when your a value is less than 1. And that's the bottom line. Okay? Let's turn the page. And so now we're going to introduce what happens when your a value or your scalar is negative. Okay? So just like in other graphs that you've done, you've had slope and then you've had negative slope, and what happens, right? It kind of reflects over itself, and so it's the same kind of idea here. The only thing that happens when you have a negative is it's going to flip over the x-axis. Here's your x-axis right here running left and right, and this graph is the graph of y equals negative 2 to the x. Now, is this graph stretched or is it shrunk? I should go back to the last page. Let me redo this real quick. Right there. This should be the absolute value of a. Okay? So if the absolute value of a is bigger than 1, you're going to get a stretch. If the absolute value of a is less than 1, it's going to shrink. So on this one, I do have negative 2, which immediately should tell you the graph is going to reflect over the x-axis, but if you take negative 2 and take the absolute value of it, you get a 2, which means this graph, compared to the parent function, still has a stretch to it, because 2 is larger than 1. You can see this graph is narrow. If it was 3, it'd be even narrower. Okay? A negative number flips it, and that's the only thing a negative number does. Okay? When multiplying a number or a scalar, the graph gets stretched or squeezed or even flipped over the x-axis. In this case, if you have a negative, that's going to flip over the x-axis. All right? This last slide, let's see, we're going to translate some graphs here. We're going to so when you see this word, I know we're kind of mixing some, this is just movements. You may hear me say the word translation or translate movements. That's up, down, left, right, okay, stretch, shrink, and flip. All right? Those are all the different movements, up and down, left and right, stretch and shrink, and flip. Those are all the translations, which sometimes we refer as translations or translate. Those are movements of a graph. That's what that means. Okay? So here we go. Look at this problem here. So what we want to be able to do over time, and this takes some time, is to be able to understand that this is the parent function, which starts right here in that light gray. Okay? And we want to be able to move it. We want to be able to move it according to what we see here. What did we talk about first? If there's a number outside, what's going to happen? It's going to move to the right 3. So 1, 2, 3. There's a negative 2 inside the parentheses. Or excuse me, I said plus 3. So we got to go up 3. 1, 2, 3. There's a negative 2 inside the parentheses. So that's going to move it to the right because we got to think opposite. 1, 2. Okay? In this thicker, bold, black line, that's the graph of this right there. That's that graph. And that should make sense. Up 3. So 1, 2, 3. Negative 2 means right 2, right 2. And I have a negative out in front, which means it's going to do what? It's going to flip upside down. And so that's why you get that graph right there. Okay? Now this one says your turn, and unfortunately I couldn't figure out a way to keep the graph off the paper, but hopefully if you can just cover it up with your hand, okay, and off to the side you can make a little XY coordinate plane and figure out what this graph would look like. Okay? So we would go down 4, 1, 2, 3, 4, and to the left 1. I always used to do this, D4L1. I used to write right above there, and then if it was whatever this number was, I'd say, okay, this is going to be a stretch. So I'd go to down 4, left 1. That's my vertex, right? This is a vertex of the graph. It's where it starts. And then this graph is going to be everything's going to be multiplied by 2. Remember, the parent function was always 1 by 1. If you go back up to this slide here, if I went over 1, I got 1 there. If I went over 2, I was 2 there. So now everything on this bottom one is being doubled, right? So you can see if I go over 1, I should go not up 1 like the parent function, but I go over 1 and up 2. Why? Because everything was multiplied by 2. And so you can just go over 1 and up 2, over 1 and up 2, and you can continue that path and go to the left 1, up 2, left 1, up 2, and you can do it that way as well. So it's a little easier because it's a grid. I know by hand you can go up 1, excuse me, to the right 1, up 2, to the left 1, and up 2, and there's your graph. And we're just doing some rough sketches right now. We want to be as accurate as possible, but we're just kind of introducing this to you so you can kind of get the idea. All right, I think we're on to the last one. So now we're going to kind of go backwards, if you will. This says, even though you don't know what this parent function looks like, this was on your front page, this is a cube root function, can you write out the equation? So I didn't give you an equation and ask you to graph it. I'm asking you to, if you can, take these translations, if you can take these translations and apply it to the function. Shifted to the left 5 units. Okay, I'm going to leave some space here, so I got the cube root of x. So shifted to the left 5 units. That's going to be what? If it's to the left, that means it's going to be a plus 5. underneath the cube root bar, down 2 units, minus 2, stretched by a factor of 3, multiplied by 3, and reflected over the x-axis. Put a negative out in front. Now, honestly, for this example, probably could have went with something a little bit more what we just got done doing. And just, instead of doing that, let's just do this one instead, okay? I wanted to show you this because the point we're trying to make, that I'm trying to make, is no matter what the function is, and you're going to learn this over time, no matter what the function is, these translations are going to carry over into every single unit. It's going to be repeated over and over again. So if I take this, for example, it'd be y equals negative 3, absolute value of x plus 5, minus 2. Shifted to the left 5 units, plus 5, down 2 units, remember it's outside, right and left is inside and always opposite. Stretched means 3, reflected negative 3. Okay? I know I went through that fairly quickly, a lot of slides to get to, and we'll talk more about it in class, and we can do more of these and give you some more practice, okay? Take care.